In this video, I'm going to review the Euler method for solving ordinary differential equations. This is something that's important for understanding how the numerical techniques work that are used for solving differential equations, and solving differential equations are very important in many areas, including reactor design. The Euler method is a version of many of the techniques that are used, but it'll help us visualize how these techniques work. So what I'm going to look at is a simple differential equation where the derivative is given as a function of both x and y. And I'm going to pick as the example the derivative of y with respect to x is 3x squared y. And then I'm giving initial conditions because all of these problems that we're going to work with are initial condition problems. Namely, at some point, x0, we know the value of y. So for our example, we'll say at x equals 1, we know y is equal to 2. The way the Euler method works is use a recurrence formula that says if I know the value of y at a certain value of x, then some increment away, x n plus 1, I can determine the value of y n plus 1 by evaluating that function. And remember, this function is the derivative of y with respect to x. Evaluating that function at xn and yn. So graphically what we're doing, the idea is if we know the value of a function at some point here, then we can calculate the value at a point close to it by using the value of the function here, the derivative here. So it's an approximation. And essentially, if we were to blow this up, I know the value of y at xn. I want to know what's the value of y at xn plus 1. And I'm going to use the derivative evaluated at xn plus 1. So it's an approximation that I would take this slope, and I'm essentially saying delta y over delta x is equal to that derivative, that function evaluated at the previous point. It's not completely accurate, it's an approximation, but if the steps are small, it's a very good approximation. Now, I've rewritten a recurrence formula here where I've put in h. This is the step size, which we normally keep constant. So this difference, xn plus 1 minus xn, we'll call h the step size. And as you can imagine, as we make that step size smaller, we get more and more accurate in our calculation of the y value. So we're going to use this differential equation as an example. And our initial conditions, our starting values, where we know the value of y is at x equals 1, y equals 2. And then we're going to make this step. We want to determine x1. So I'm going to use a step size of 0.1. Probably too big to be very accurate, but helps us to visualize what's happening in the calculations. So that means x1 would be 1.1. y1 is y0 plus h times the function evaluated at the previous point. So that means y1 is 2.6. So now with x1 and y1, we can take our next step. x2, we're at 1.2. y2 now is y1 plus h, and now the function is evaluated at x1 and y1. So our new y2 is 2.915. I've written down the next step, and we can continue doing this and get y at any value of x. We make enough steps. Well, we can be much more accurate if we made h 0.01 or 0.001. And certainly with computers, even just a spreadsheet, we could do that type calculation. And this is how visualized differential equations are solved. What we can do in more sophisticated methods is make better approximations instead of calculating the function at just the previous point. And we'll show another video how that's done. But this helps visualize when we solve reactor design problems, for example, where we have a plug flow reactor and we have material flowing in and we want to know conditions at the exit and at the entrance, say distance z equals 0. We know, call this our initial conditions, we know the conditions for concentrations, and we'll divide the reactor into a bunch of small volumes and calculate using something like the Euler method. We can calculate conditions at the exit of the reactor.